I found a way to measure distances in Genshin Impact almost anywhere, even if you don't have navigation. The key that makes all of this possible is this. Hello, Count Sacke here, back with another Genshin Impact video. Today, I'll be discussing on how to calculate distances in Genshin Impact. We'll have to go through quite a bit of physics, but I promise it'll be worth it. On a side note, this video is also going to be used in an upcoming very large video series project that I believe will be my best work yet. Just something for you to look forward to. Anyway, back to the main topic. Yep, the way we calculate distances is as simple as moving. Wait, no, not that one. Okay, let me rephrase. It's as simple as moving without sprinting. In order to explain how and why simply moving is the key to measuring almost any distance in the game, we need to talk about some physics, specifically kinematics. There are countless lectures and videos about the basics. However, finding videos with more detail and complicated topics is harder to come by. The thing is, the more difficult topics are actually more applicable to this scenario. Don't worry though, the resulting math is actually pretty simple. It just takes some time to get to it. How do we describe movement? This is the question that kinematics tries to answer. For that, kinematics is defined as the study of motion. When we say that an object moves, we observe that its position changes. However, to fully describe the motion of an object, we need to know what direction the object was moving and how far it went. Lucky for us, math actually has something that does exactly what we need. We have a quantity called a vector. Vectors can be geometrically represented as arrows. Arrows point in a specific direction and have an associated length. To be technical, vectors have both direction and magnitude. We can multiply vectors with scalars. They're called scalars because they literally scale up or down the vector. As said in classes, scalars only have magnitude, so they're just a number. Geometrically, what this does is increase or decrease the length of the arrow. Interestingly, if you multiply a vector by -1, it flips the vector to point in the opposite direction but maintains the same magnitude. When we add vectors, geometrically it can be shown as placing them tip to tail, as commonly said. We then draw a new vector from the tail of the starting point and to the tip of the end point. Another useful thing that vectors have are components. The components are a set of scalars which represent a vector in a specific coordinate system. For our case, I'll stick with Cartesian coordinates for now since it's what we're most familiar with. You might ask, why can a vector be represented with scalars? What do numbers that shrink or elongate an arrow have to do with it? The reason is this. I mentioned that the value of the components for a vector depend on the coordinate system used. We can think of any vector in space as the sum of vectors that define the coordinates we use. These vectors that define the coordinates are called basis vectors. For Cartesian coordinates in 3D space, we actually have 3 basis vectors. Each of them point along the x, y, and z axes respectively, and all have a length of 1. These are denoted as x hat, y hat, and z hat shown in the video. If we scale these basis vectors, then add them up, we can actually create new vectors that aren't just lengths of 1 away from the origin. These numbers that scale the basis vectors are scalars and are the components. If I have a vector u with components ux, uy, and uz, we can express vector u as ux times x hat plus uy times y hat plus uz times z hat. We can see that each of these terms, or components, are multiplied with their basis vectors, which add up to vector u. When we're dealing with addition and subtraction of vectors, we add or subtract them component-wise. We can show this algebraically. Consider the addition of two vectors u and w. We can see that ux and wx share the term x hat, uy and wy share the term y hat, and uz and wz share the term z hat. This means that we can factor those respective terms out and we're left with the following. Geometrically, we can also see how this works. Each component vector gets added onto each other, and then, well, just putting them tip to tail as usual will give you the resulting vector sum. Alright, let's get back to kinematics. To describe position, we use a vector. This vector starts at the origin and ends at the point it refers to. For our case in Genshin, we actually have knowledge about the path the traveler took. So, we have a collection of positions each at a specific point in time. There can be some sort of position function with respect to time, so r of t, or we can just call it r, which outputs the traveler's position at any moment in time. If we were to plot this function on an xy plane, we can see the path the traveler took along the horizontal plane. Position is useful to understand where an object is, but it doesn't give much information about how the object moves. What we use is something called displacement. Displacement, delta r or s, is defined as the change in position. Displacement does not care about how it got to the current position. It only knows where the object used to be and where it is now. This is in contrast to distance. Distance only cares about how far an object traveled in order to get to where it is now. A short way of saying this is that distance traveled is path dependent, whereas displacement isn't. Another difference between the two is that displacement is a vector quantity, whereas distance is only a scalar. At the heart of the math behind kinematics is calculus. If there's anything to know about calculus, it is the mathematics of change. Since change is an inherent part of motion, I think you can see the connection. The problem is that this video would be way too long if I taught it here. However, there is one thing I need to establish. This is a derivative. The d dx shows that we're considering the change of f over the change in x. df dx is said as the derivative of f with respect to x. If you can understand that, you can read Leibniz notation. Velocity is defined as the derivative of displacement with respect to time. This means that it quantifies how much displacement occurs over a short period of time. We can also interpret this as the change in position over time. They end up being mathematically equal to each other. Typically with derivatives, we would associate ds as a change in displacement. However, this makes things weird. With ds being a change in displacement, velocity becomes the change of position over time. This statement doesn't exactly make sense. I personally believe a better interpretation for ds is a small displacement. With ds being a small displacement, velocity just becomes a small displacement over a change in time. I just want to get that clear because I tend to get confused about it every now and then. When we calculate the velocity, we actually get something called the tangential velocity. The tangential velocity points in the direction the object is moving. When we say tangential, we just mean that it only intersects the path at one point. The last variable we'll be considering is acceleration. Acceleration is defined as the derivative of velocity with respect to time. This describes how much an object's velocity changes over time. The interesting thing about this is that acceleration is split into two different vectors: tangential acceleration and normal acceleration. Normal acceleration describes rotation or turning, while tangential acceleration describes changes in your velocity along the forward and backward direction. It's pretty common to hear in introduction to physics classes that it's possible for an object to be accelerating but still move at the same speed, or the magnitude of the velocity is still constant. The reason why you're accelerating is because the velocity is changing, and the velocity is changing because the velocity vector can also rotate. It is a vector, it has direction and magnitude. Your magnitude may be constant, but its direction may be changing. In this scenario where your velocity magnitude is constant, the tangential acceleration is 0, but the normal acceleration isn't. All that said, we end up with a second-order differential equation. If we use integrals, which are basically a form of fancy addition, we can derive equations for velocity and displacement. In general, velocity is equal to the integral of acceleration with respect to time. and displacement is equal to the integral of velocity with respect to time. The reason why we're going into all of this detail is because how we measure length actually depends on how the player moves. We need to be able to account for all different types of paths the player could trace out. When we're dealing with objects with more complex motion, or curvilinear motion to be more precise, Cartesian coordinates can sometimes make things more difficult. Rather than focusing on the entire movement along the x, y, and z axes, instead, maybe we can just focus along the normal and tangential directions. By doing this, we've actually simplified our math by quite a lot. One complication is that we want distance, not displacement. Note that distance is not the magnitude of displacement. Sometimes they can be equal to each other, but in many cases they're not. I mentioned earlier that displacement only takes into account the change in position. So if I walked up like this, then to the left like that, the net displacement doesn't care. It only cares about the initial and final positions. So in the end, the displacement vector just looks like this. A straight arrow from the starting position and the end position. It doesn't even look at the rest of the path. However, distance does care that we traveled that specific path. This means that we're kind of missing something. Let's break down our path into very small segments across time. These segments are dl, where L is the length of a segment. At the edges of each segment, we have 2 points, r of t and r of t plus dt. We can see that at this small scale, dl is approximately equal to the displacement vector magnitude. If we add up the displacement vector magnitudes of all the tiny segments, we calculate the total length. There's just one thing about this equation. Line integrals are kind of annoying to calculate. This is a sign that we should probably stop thinking about the path in 3D space, and again, this goes back to the issue with focusing on Cartesian coordinates that I mentioned earlier. Instead, let's focus on time. How fast were we moving at a specific point in time? Recall that velocity is the derivative of displacement with respect to time. With this relationship in mind, we can focus on the magnitude of the displacement and tangential velocity. And recalling from earlier that a tiny displacement is approximately equal to a tiny change in length, we can essentially equate this to the magnitude of the tangential velocity multiplied by a small change in time. This gives us the general equation for calculating distance traveled. L is equal to the integral of the magnitude of the tangential velocity with respect to time. Just note that the tangential velocity should also be a function of time. To use this equation, we need to know how fast the player was actually moving at any point in time. Going back to Genshin, this actually isn't that hard to predict as well. The player tends to move at constant velocities most of the time anyway. I personally don't want to account for sprinting as it makes the math and equations much more harder, so yeah. If we assume that the player always moves at a constant speed throughout the entire measurement being considered, then the tangential acceleration magnitude is equal to 0, and this implies that the tangential velocity magnitude is a constant. Therefore, the length is just really equal to the integral over the time period considered for the measurement of the tangential velocity magnitude with respect to time. And well, since the velocity magnitude is constant, it really just ends up being this. L is equal to the tangential velocity magnitude times delta t, which we say is the measured time. However, I won't deny it's much easier to measure distance if you start from a standstill. There are some cases where the acceleration cannot be ignored, so here's the equation. You start off with the tangential acceleration magnitude being a constant. From here, we can do integration of the acceleration with respect to time to calculate the tangential velocity magnitude. Since the acceleration, or the tangential acceleration magnitude, is constant, it just becomes the tangential acceleration magnitude times time plus a constant, and that constant happens to be equal to the initial velocity. From here, we can take the integral of the tangential velocity magnitude with respect to time once again, but this time we get a different equation because our velocity is no longer a constant. Instead, what we get is this. L is equal to the tangential acceleration magnitude multiplied by delta t squared over 2 plus the initial velocity times delta t. There's one last technicality I want to mention before we move on. The velocity and acceleration I've been referring to in this video are actually called instantaneous velocity and acceleration. The other type is actually called average velocity and average acceleration, but I don't use it here because they suck anyway. Before we can properly calculate distances, we actually need to determine the speed, as its value is basically dependent on the magnitude of velocity, which is speed. I was actually quite surprised to find that KQM doesn't have numbers for how fast the player actually moves. They do have these values in the evidence vault, but I'm confused as to what they are associated with, like what type of movement is it, and either way, we're not looking for any dashing or sprinting, so it's not really that useful for us. I've also tried looking around other places, but they just keep mentioning that different character models move faster than others, but I'm looking for specific numbers. Because for some odd reason no one has ever bothered to measure this, I'll just have to do the experimentation, data collection, and analysis myself. Luckily, I have experience in that. From our derivations, we can calculate speed with the following formula. The tangential velocity magnitude is equal to L divided by delta t. If we assume that no acceleration occurs within the time period, or if the acceleration lasts for only a very small duration, then this formula is applicable. I believe the formula works as a pretty good approximation for walking, jogging, and gliding downward. However, I believe for gliding horizontally, the acceleration is not as negligible. The issue is that we don't know the value for our acceleration, however, there is a way to determine it. Take note, we're only concerned with the tangential component of acceleration, not the normal component. The reason why is because speed only changes with tangential acceleration. We know that if we start from a standstill, our initial velocity is 0. We also know that after moving a bit, the speed reaches a constant value. Therefore, we just need to measure either the time taken to reach that constant speed or the distance traveled. However, it is very difficult to eyeball once the player reaches a constant speed, and it's also not exactly very easy accessible to measure distances. Plus, you have to take into account that the navigation doesn't update every frame or so. If we assume that the acceleration and deceleration are equal along with the time spent accelerating and decelerating, that will be much easier for us. We know we'll start decelerating once we let go of the forward button. Then from there we can measure how long it takes for the player to stop moving altogether. This means that we can actually use this formula to determine the acceleration and deceleration. The acceleration is equal to the change in velocity divided by the change in time. Now, here's the thing. We also now need a new equation for distance traveled. The reason is because we have 3 different motions: acceleration, constant speed, and deceleration. To derive the equation for it, we can split up the motion into 3 separate parts, and each of them are labeled 1, 2, and 3 for acceleration, constant speed, and deceleration respectively. I'll define some variables. Delta t will be equal to the total time measured, including the acceleration and decelerating. TA is equal to the time spent accelerating and/or decelerating. V is equal to the tangential velocity magnitude, and A is equal to the tangential acceleration magnitude. We have to integrate over all time periods to calculate the total distance traveled. By properties of the integral, we can actually split up the integration into 3 different sums by just changing the upper and lower bounds for the integrals. This means that L is equal to L1 plus L2 plus L3. And, well, L1 is equal to the integral from 0 to TA of the tangential velocity magnitude times dt, plus the integral from TA to delta t minus TA of the tangential velocity magnitude times dt, plus the integral from delta t minus TA to delta t of the tangential velocity magnitude with respect to time. For the first integral, the tangential velocity magnitude is equal to the acceleration times time. For the second one, since the velocity is constant, it's simply equal to v. And the last one, it is equal to minus at plus v. The reason why the negative sign is there is because the velocity magnitude actually decreases at that point. And after doing a bunch of algebra, we end up with L is equal to v times the quantity delta t minus ta. We can see that if ta, the time spent accelerating, is very small, then L is approximately equal to delta t. Some of you already know that characters have different movement speeds based on their gender and height. A video by Keacs demonstrates this very nicely in a video called Hidden Genshin Impact Movement Mechanics. Explore the world faster. Here's a table that shows the different types of base models. We can use the equations from earlier to calculate the speed and acceleration. Let me now talk about my methodology. Using the quest on the stage behind the stage, I turned on navigation for it. Yes, I haven't started the quest yet, but I'm glad I haven't. The navigation brings me to Tea-Master Liu Su, and you know the best part? It doesn't pull me into a cutscene when I get close to him. On top of that, the area around him was flat and allowed me to find a consistent setup. These stairs were a great spot to pinpoint 10 meters away from Liu Su. While messing around, an amazing thing I realized is that the prompt to talk to an NPC only pops up once the player is 2 meters or closer. This is a very big deal because it tells us that at the frame where the prompt to interact with the NPC appears, we're exactly 2 meters away from Liu Su, or approximately, since how game frames update. In order to measure distance, we'll have to use the navigation tracking values, and it depends on which type of motion we're considering. I'll be considering walking, jogging, gliding while falling, and gliding horizontally. To measure time, I use OBS to record my gameplay, then DaVinci Resolve to get the number of frames it took me to travel the distance. I also know that I use 60 FPS, so that provides me an easy conversion. The characters I chose for the experiment were the following: Aether, Amber, Kaya, Lisa, and Diona. I chose the starter characters because everyone should have them, so yeah. Unfortunately, we aren't given a short female model character for free, so I just decided to go with Diona since Amber, Kaya, and Lisa are from Mondstadt. For the procedures, it depends on the motion we're doing. Let's start off with the walking and jogging speed measurement procedure. 1. Position the player at the stairs as shown. 2. Start recording the video. 3. Look directly at Liu Su. 4. Move towards Liu Su. 5. Keep moving for a bit after the prompt to talk to Liu Su appears, then stop. 6. Stop the recording. 7. Go into the editor and measure the time taken to travel the distance. For the distance, this is pretty easy to calculate. You start 10 meters away from Liu Su, and we stop our timer at 2 meters, so the distance traveled is 8 meters. For the gliding fall speed measurement procedure, 1. Position the player at this roof. 2. Start recording the video. 3. Once the player is off the roof and falling, open the wind glider. 4. Wait until the player touches the ground. 5. Stop the recording. And 6. Go into the editor and measure the time taken to travel the distance. The reason why I chose this specific spot for this test was because I could measure 2 points which are vertically aligned with each other. One on top of the roof and the other one directly on the floor. This means I could use the Pythagorean theorem to calculate the height. For the horizontal gliding speed measurement procedure, 1. Position the player at this roof overhang. 2. Start recording the video. 3. Face directly towards Liu Su and move forward. 4. Once the player is off the roof and falling, open the wind glider. 5. Keep moving forward past Liu Su. 6. Wait until the player touches the ground. 7. Stop the recording. And 8. Go into the video editor and measure the time taken to travel the horizontal distance. Now, since we're only concerned with the horizontal movement in this one, we actually don't use the distance traveled, we use the horizontal placement, or delta x as I've drawn. I found that this value was consistently 5 meters for all characters. It might be different, but we don't have enough precision to actually say for sure. Lastly, I decided to only take 5 samples of each. Since this is per character, and for each type of movement, we need to collect 100 values of data. After going through all of that, here's a table with my results. And here's a bar graph for also reference. From these measurements, we can see some things that we can expect based on previous observations. For jogging or normal ground movement, tall males are the fastest, and it decreases as the character models get smaller, so yeah. Do also note, we're not doing any sprinting or dashing. For walking, I was actually surprised to see that tall females are actually the fastest. The standard deviations are pretty low, so it's kinda unlikely to be a fluke, even if my sample sizes are quite small. Lastly, for the gliding movements, they don't seem to vary between character models, so that's cool. Because the different models all have the same gliding speeds, this cuts down the number of samples that I need to collect for the next experiment. The next experiment is to determine the time of acceleration. What I did was to simply move forward and stop while gliding. I used the streamlines left by the glider to gauge the acceleration. If the streamline is curved, acceleration is occurring at that point. There is a bit of distortion on these streamlines, but you can still make it out. The procedure was quite simple. 1. Find a location high enough to open the wind glider. 2. Start recording the video. 3. Jump off and open the wind glider. 4. Make sure the player isn't moving, then move forward for a bit and stop. 5. Stop the recording. 6. Measure the time of acceleration using a video editor. This resulted in an acceleration time of 0.18125 seconds. I do hope someone can find a way to potentially increase the accuracy of the speed measurements. Keep in mind that the navigation distance doesn't indicate decimal points, so there's a loss of accuracy in the distance measurements. Plus, on top of that, the distance in the navigation doesn't actually update in real time. Regardless, I think these are a good enough starting point, given that no one that I could find has bothered to get a number of some kind. If you skipped straight to this part, I want to greatly emphasize that you're measuring a path distance. Whatever path your character traveled, this calculation obtains the length of that path. If you're trying to measure a straight line on ground, be mindful of slopes or being slightly at an angle. These discrepancies add up, resulting in errors, and become more exaggerated, especially over long distances. All in all, be careful when doing your measurements. To measure a distance, it's as simple as measuring the time taken to travel the path. Use the corresponding equation, velocity, and acceleration for a given character base and motion. Input the measured time, and from here, just compute the value and you have calculated your distance of the traveled path. The approximations are best used for times greater than maybe about 2 to 3 seconds. I actually have something I would like to mention. When getting the measurements for distance, I didn't know about the Sumeru Commission. Meow. Meow meow. 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 What a name. Anyway, this has a much more accurate distance indicator than the Quest navigation. It updates the distance more frequently, and it's something that everyone has access to with good RNG. To end off this video, I'll perform a demonstration for how you can do this yourself. Hello everyone, it is me. So basically I will be doing a demo for how to do measurements in this case. So basically what I want to do is to measure the diagonal length of these stairs. They're quite long, and well, yeah. Now, the first instinct some of you might have is to just, well, measure it by running across, measuring the time it takes to go across this, and well, yeah, then just calculate, input your speed, and then boom, you'll have your speed, you will have your distance. Unfortunately, that doesn't exactly work because, well, if you observe with me for a minute, look at how the speed changes when I start to go on the slope. So you can see that there's a pretty significant change in the speed as I go onto these stairs. Now, that's just due to how games tend to handle like movement of characters and such. It's to like help prevent like flipping through walls and such. So how exactly can we measure this? Well, if we remember some basic algebra, all we really need to do is to measure the vertical height and horizontal length of a triangle to get the hypotenuse. Now, there are many ways we could actually measure like the height, and there are some other ways we can like measure the length, but I want to do it in a specific way by hitting two birds with one stone. And that is just by doing gliding. Of course, it would probably be easier for me to set up by just doing some running along the side wall of this, but I personally would feel like I don't want to do that, and I just genuinely think it would be a little bit more interesting to see me do it this way. Because it also allows me to explain something. When I fall, if I fall without moving, it takes some amount of time, but if I fall and move around like horizontally and whatnot, it still takes me the same exact time to hit the ground. What this basically means is that your horizontal and your vertical components for your velocity are independent of each other. So I could be like doing whatever the heck I want mid-air while gliding or even while just falling in general. It doesn't matter. The only thing that matters is how far horizontally you move, but it doesn't change how fast vertically you fall. And the reason why this is the case is because, well, we have X, Y, and Z coordinates. Unity also uses X, Y, and Z coordinates, which is the game engine Genshin runs on. We have XZ for horizontal and Y for vertical. The XZ components do not affect how fast you fall along the Y direction. So that's very important. That's very useful for us because that means that we can hit two birds with one stone by just going horizontally like this. We can measure both the vertical height and the horizontal length without having to do two separate takes. We can do it in one sample. We have to make sure we're aligned properly. If I'm at an angle, well, I'm going to exaggerate this, but if I'm at like an angle like this or something, you can clearly see that I'm not actually measuring the horizontal length like this. So yeah, it's very important to make sure that I get the alignment correct. So what I'm going to do is I'm going to use like these little lamps to determine if I'm far enough horizontally. And I'm also just going to, align myself here, and then I'll face towards the side like this. And well, let me just make sure that I'm at the top of the stairs. And well, yeah. So yeah, here's what my sample is going to be. I'm just going to jump, and there we go. Keep going, keep going, keep going, keep going, keep going, keep going, and stop. There we go. So now I can use that as my sample for measuring the horizontal length and the vertical length. So yeah, I'll see you in my video editor. What I'm going to do is basically, measure the horizontal and vertical. Basically, I'm just going to drag my thing into the timeline, and I'm going to automatically mute that because I don't want to hear myself talk. Just go to where I collected the sample. So this is going to be towards the end. I'll just cut all that out so that way we don't have to deal with like a ton of clutter. I'm gonna go through this frame by frame. Alright, so unfortunately we do actually lose a bit of distance here, so that's something I did not take into account. We actually lose a bit of distance by jumping forward a bit. I think we can approximate this as like an extra 1 meter distance. So it wasn't exactly as pretty of a solution as I thought initially. That I've only now realized it, so that's my fault. But again, the accuracy of our measurement is only as accurate as our velocities and the accuracy of your timing. So yeah, it's not exactly, you can't exactly expect to be the most accurate. So here I'm gonna start like right, we'll go maybe a frame before. So we'll start a frame right before I open the wing glider, and there we go. So we'll then just let it play out, and when I stop moving, that is what we're going to measure the time it takes for this. I think we can pretty easily see that like Raiden Shogun is like stopping like around here. So I think this is a pretty good stop. I don't need to do a marker. I can just do it like this. So I'll put a mark right there, and then I can like measure the length of this, which in DaVinci Resolve it will show in time, or I could do frames. Technically time would be useful, but this second number here is in frames, so I like to use this one. So this is at 267. So we can actually pretty easily convert this to frames per second by remembering that, hey, wait a minute. Oh yeah, I have 60 frames every second. So yeah, there you can see the units, like the units cancel out. So here we have the frames cancel out and we're left with seconds. So what we should get is 4.45 seconds. So whatever distance we calculate from this, I'm just going to add like 1 meter for a bit of extra, just to account for that distance that I skipped over. I'm going to undo that cut, then I'm just going to wait all the way until the wings just disappear. So that'll just be the time it takes to touch the ground. So wait, I'm going through this frame by frame. Frame by frame. Oh, the wings disappeared. And there we go. So the frames disappeared at this point. So we can now measure the time, which is 382. Now, both of these horizontal gliding stuff, whatever, the value we calculate for our distance, I'll just say Lx. What we just do is we need to just know which velocity we use for this, so I'll just put that as x for now, delta x, and we also have one for the y component, y, py, delta t. And I'm going to be using the approximation formulas because again, these aren't exactly the most accurate. We're not going for like extreme precision on everything or extreme accuracy on our measurements. So let's take a look at our speed table. So we have all these different types of variables. Raiden Shogun is a tall female, and well, we can make use of our gliding falling speed, which is 1.837. So now let's calculate for our horizontal distance. So again, we'll bring up our little table here. We're using a tall female. Raiden Shogun is a tall female model. Then, well, we want to do glide horizontal 5.315. 652 meters. So yeah, there we go. So now we can very easily do our Pythagorean theorem. So we know we wanted to measure the length, and we basically have something that looks something like this. We have this one, which is our L. And I think we should be able to pretty much tell, hey, this is not too hard to do. We have some basic algebra we're going to do. We do it. L squared, Lx squared, Ly squared is equal to L squared. And well, just take square root. Technically there's a positive and negative, but we don't take the negative because lengths don't exactly, they're not exactly negative, so they're positive. So yeah, anyway, enough about that. We can just simply take our two numbers here. So this number squared plus this one. (286 meters). And while we're at it, we can also measure the angle here, which is this angle here. So let me just indicate this with the proper arrows. And we can also measure this angle theta here. So we can measure angle theta by doing the tangent function. So the tangent theta, it's going to be the opposite, so that's Ly, and we have divided that by Lx. We can get theta by doing the arctangent function, so .382 degrees if you want to be more decimals. So yeah, we can actually calculate quite a bit of stuff just by, measuring this distance and stuff. And you can even determine what this last angle is if you want to remember that, hey, 180 degrees for a triangle. I hope that you found this video quite interesting. It was something that I really want to do. And for those of you who want to know, my upcoming series that I made this whole entire video for, it is going to be using this method for measuring stuff. It's very important for that. I don't know if it's going to be my next video for sure. It might not be my next quality video. It might actually take a while for that. But I do hope that you're all looking forward to it. Anyway, enough about that. So yeah, that's really about it for now. So thanks for watching and hope you've enjoyed.